Now we're going to go into the second part of the week 2 agenda, which is measures of dispersion, which is actually chapter 4. And by the way, if you're worried about chapter 3 and all the other details in chapter 3 that I didn't talk about, you're not really responsible for them. I kind of take a kind of pipeline approach to the teaching here. I kind of focus on the key essential elements that you kind of need to know here, and especially for these first two chapters, don't go into all the permutations and possibilities. Just want to kind of prep you for the important part of the class, which is learning the key statistics. So that's what I have to say about that. So chapter 4, so dispersion. So let's go back to that data set just one more time. So data set 1, 1, 2, and 3, data set 2, 1, 3, and 5. They're both populations. If you remember that there are only 3 people in each one of these two classes, so they represent everybody. If I were to ask you, are these data sets equivalent or different in terms of measures of central tendency as we review, you'd probably say, well, they both have the same mean attitude, so attitude is about the same for the two groups. But what if I were to ask you, are they really equivalent groups? So that question might be, what about their dispersion? Is the dispersion in these two groups same or different? So dispersion is a way of asking about how spread out or non-spread out the scores are. As you just eyeball things, does it look like one group has more dispersion than the other group? Hopefully most of you said that the JMU group looks like it has more dispersion in it. The scores are more spread out. One of the simple ways of measuring dispersion is the range. And if you actually look at the Mary Baldwin College scores, which are just made up here, the range goes from 2 to 4, so it's about 2. The data set for JMU has a dispersion of 4. So one measure of dispersion that we almost never use, but we can talk about here just for a minute, is the range. A range is a measure of dispersion, and if a number is higher for dispersion, it means there's more variability in that data set. Now, another thing that psychologists sometimes like to do is they like to get the deviations from the mean. Of course, deviations has many different interpretations. So I'm going into abnormal psychology, if you catch my drift. This is a statistical one, but let's try that just for a second. The sum of the deviations from the mean. So I put x, that's a score, minus mu, the mean. So let's get the sum of the deviations for the Mary Baldwin group. So you would have to take the first score, 2, subtract it from 3, and you get a score of what? -1. Then you do the second score, 3 minus 3, and then you'd get the third score, 4 minus 3, and then you would add them all up. So what are going to be the sum of the deviations from the mean for that group? Well, if you add a -1, a 0, and a +1, you'll get a score of 0. So data set Mary Baldwin, for that population, the sum of the deviations from the mean are going to be 0. Let's see if we can get a higher number, maybe for data set 2, the JMU group. Did you figure that one out? 1 minus 3 plus 3 minus 3 plus 5 minus 3. What is the sum of the deviations for that one? Hopefully you got the sum of that being 0. Now, does that mean this is a useful way of measuring dispersion, the sum of the deviations in the mean? Hopefully you would answer no. The sum of the deviations from the mean for any group is always going to be what? 0. Because you're getting a negative, you're getting a 0, and you're getting a positive. Any 3 numbers, any data set in general, if you get the deviations from the mean, the negatives cancel out from the positives. So the sum of the deviations from the mean are always going to be 0. So that might be useful theoretically for a statistician, but in terms of measuring dispersion, that won't really be any good. The range is more useful than the sum of the deviations from the mean. But we're going to try one other thing that statisticians really like to use, especially people in psychology. We're going to try to get the sum of the square deviations from the mean. So the sum of the square deviations, take each score, subtract it from the mean, and square it, and then add it up. So let's try the sum of the deviations from the mean for the Mary Baldwin group. So you start with the first score, 2, minus the mean, 3, and then you get that result and you square it. So what is that result? 2 minus 3, quantity squared, is 1, plus the second score, 3 minus 3, quantity squared, so it's 0 squared, which is 0. And then finally the third one, 4 minus 3, quantity squared. So when you square everything, you only get what kind of numbers? Positive numbers. So the sum of the square deviations for the Mary Baldwin group, 2, 3, and 4, the sum of the square deviations is 2. So that's at least a non-zero number. So the sums of squares for the Mary Baldwin is 2. See if you can do the same thing for the JMU group. If you need to pause the YouTube thing here, that's fine, but I'll go right into it as well. So you would take the score of 1 minus 3, quantity squared. 1 minus 3 is negative 2, squared is 4. So it's 4 there, and then 3 minus 3, which is 0, squared is 0. And then 5 minus 3, quantity squared, is 2, squared is 4. So you should get, for the sums of squares for data set 2 for the JMU group, the sum of the square deviations is 8. So we got 2 for the sum of the square deviations for the Mary Baldwin group. We got 8 for the sums of squares for the JMU group. Is this useful? Most statisticians would actually argue yes. Because remember when we looked at this originally? We said when we looked at this originally that when we looked at the JMU group, there was more dispersion, more variability there than the MBC group. So the fact that we got a sum of the square deviation for the JMU group at 8 and the sums of square deviations for the Mary Baldwin group at 2 is mapping that pretty well. One number is higher than the other. So the sum of the square deviations will actually be a very useful formula for doing statistics. So the follow-up learning, to kind of wrap things up, let's say that we gave you another question. We have a population of 3 people at JMU with attitude scores of 3, 5, and 7, and 3 at MBC with attitudes of 1, 4, and 7. Who has the better attitude and which group has more dispersion in their data? If you want to pause the tape for a minute and think about this and then try to turn it back on, you can. Who has the better attitude? Well, the measure of attitude is central tendency. Which measure would you use? Usually people use the mean. So it looks like the JMU people have a better attitude. 3, 5, and 7. The mu there is 5. For Mary Baldwin, the mu there is 4. Which group has more dispersion? Well, if you went and did the math once more, you could do the range, but we don't usually do that. And you could also do the sum of the deviations from the mean, but that's going to be 0 both times. If you got the sum of the square deviations, if you have 3, 5, and 7, if you do the math for that, you probably come up with the sums of squares at about, 8, because it's just like the previous data set. Or so I thought the 1, 3, and 5 dispersion is the same as that one. So sums of squares of 8, and if you look at the 1, 4, and 7, you probably get something like 18, because 1 minus 4 is 3, squared is 9, and the same of 7 minus 4. So you've got more dispersion in the Mary Baldwin group than you do with the JMU group. You always know that if you get a negative value when you do the sums of the square deviations that you did something wrong. But hopefully now you understand from the first 2 lectures here that when we look at any data set, we like to look at the measures of central tendency, mean, median, and mode. Mean being the most useful. We use the median when there is an outlier. And then the other thing we look at with any data set besides its central tendency is the dispersion. We can use the range, but don't often use it. The sum of the deviations from the mean is always going to be 0. The real useful one that we like to use is the sum of the square deviations. You get rid of all the negative values, and the more dispersion in the data set, the larger that number will be. So hopefully this makes sense to you as well. Thank you very much.